All right, so I lost my original video, so we're going to proceed with a reshoot of the notes here. My class didn't get through the 4.2 notes. We got up to the free response question, and we answered those today in class. We had already done 1999 BCA, example 5 here, letter A. We had done that one. All right. Again, read through the table here. We've got the rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. So these are rates in the table, not the actual amounts. This is the rate of change of the amount of water flowing out of the pipe at different times, measured at different times. So it's measured every 3 hours for a 24-hour period. Okay. So letter A, we were asked what is the minimum number of times t, 0 less than t less than 24, in which the flow rate is 11 gallons per hour. So when we went over that question yesterday, we looked at the different intervals that we had here, and we saw that from 10.8 to 11.2 for certain, right? We got to get from here to here, we have to cross through 11. So at some point in that time interval from 6 to 9, we then are going to have a rate of 11. Likewise here from 11.3 down to 10.7, we also will have to cross through 11 at some to get from here to here. Now, that's the two for certain that we know the number of times where we cross through 11, but it doesn't mean that that's the only time. I mean, for example, here in this very first interval, yes, we start at 9.6 and it ends at 10.4, but we have no idea if from this, between the hours of 0 and 3, if we go up, up to 15 gallons per hour and then back down to 10.4. We have no idea, okay? So, overall, we have an increase here just from 9.6 to 10.4. We have no idea what's happening between. But for certain, from 10.8 to 11.2, 11.3 to 10.7, we know we have to cross 11, okay? So what theorem allows us to state, that we're going to cross all of the intermediate values between two numbers if the function is continuous? Well, that's the intermediate value theorem. Okay, the explanation here, while not like pretty or succinct, is sufficient. I'll wait. Okay, so we'll say 2 times. R is continuous for 0 less than t less than 24 because R is differentiable for 0 less than t less than 24. Okay, in order to use the intermediate value theorem, you must show that you have met the necessary requirements to use the intermediate value theorem. Intermediate value theorem requires that our function is continuous. In order to establish that the function is continuous, okay, we just need to state that it's differentiable, right? Because that's what we're told here. The function is differentiable, so therefore it's also going to be continuous, right? That's one of the properties we know of differentiability. It implies continuity. Okay, so now, once we've established that, we can then say, okay, since R of 6 is less than 11 and R of 9 is greater than 11, and since R of 15 is greater than 11 and R of 18 is less than 11, then the intermediate value theorem guarantees that R is 11 in those two intervals, or the intervals from 6 to 9 and intervals from 15 to 18 there. Okay, now letter B is also in existence. It's asking, is there some time 0 less than t less than 24 such that r prime of t is 0. Okay, the answer here, right? Well, so what are we supposed to use? What thing do we have that allows us to say that our derivative must equal 0? What theorem allows us to say that? Well, that's the Rolle's theorem, right? Rolle's theorem says that if we meet the certain conditions, we can say that our derivative is going to equal 0 at some point, okay, in our interval. So what are the conditions for Rolle's theorem? There are 3. 1, the function must be differentiable. We know that already, okay, that it is. We also know the function must be continuous, and it is, again, because it's differentiable, it's also continuous. And finally, the endpoints must be the same value. So the endpoints of your interval must be the same value. So we're going to look at R of 0 and R of 24, and sure enough, they are both 9.6. And so we are able to then use and apply Rolle's theorem here. Now, it doesn't have to be that we use the endpoints of the interval 0 and 24. We could use an interval within our table here to also, identify, two places where the y values would be the same. Unfortunately, though, there's no other rates here that result in the same and the same value. Okay, they're all different values except for the endpoints, the 9.6. Okay, but for example, if like 3 was 10.4 and 6 was 10.4, you could also use that interval to show, or to use Rolle's theorem, and then also to show that there would be a c value that exists such that the derivative would be 0. So once we've established these three things, r of t is differentiable and thus continuous on the interval, r of 0 is equal to r of 24. So by Rolle's theorem, there exists a c value, 0 less than c less than 24. So in other words, c is between 0 and 24, such that r prime of c equals 0. Okay? And then letter C, is there some time t, 0 less than t less than 24, such that r prime of t is equal to negative 0.2? The answer, of course, okay, is yes here. Well, not yes, I guess. It's not so obvious, is it? So how do we do this one? Well, does Rolle's theorem work here? Well, it would not, right? Because Rolle's theorem only guarantees that the derivative must equal 0. We don't have, we're not able to use Rolle's theorem to guarantee that the derivative must be negative 0.2. However, we do have the mean value theorem, okay, which is in existence for the value of the derivative at, for specific values of the derivative, okay? So the mean value theorem states that the average rate of change is equal to the instantaneous rate of change, or the derivative, at some point in our interval, okay? So what we can do is kind of like carefully or, intentionally choose an interval whose average rate of change is negative 0.2. Okay, one such interval is from 15 to 18. Okay, from 15 to 18, you're going from 11.3 to 10.7, which is a change of negative 0.6 in gallons per hour for the rate, but it's over 3 hours change, so it's negative 0.6 divided by 3, so we get negative 0.2, which is the exact rate that we want. So by the mean value theorem then, we are guaranteed that there is a c value between 15 and 18 such that r prime of c is that negative 0.2 that we're shooting for. And that's how we can answer that question. So again, how do we answer it fully? Yes, answer the question, right? Yes, and then justify. R of t is differentiable and thus continuous on 0 to 24. Again, that's like the prerequisite for the mean value theorem, or the conditions to use the mean value theorem. We then show, okay, since r of 18 minus r of 15 over 18 minus 15 is negative 0.2, then the mean value theorem guarantees there is a c such that r prime of c equals that negative 0.2. Okay, the derivative must equal that average rate of change somewhere in that interval there, for c value somewhere in that interval. Okay, and so that creates the answer there to our question. So the justifications, you want to make sure that you are establishing that the prerequisites have been met before you then, use the mean value theorem, or use Rolle's theorem in these cases, or use the intermediate value theorem. All right, moving on. All right, there's this exploration that I gave my students time to work on, but of course you can pause the video right now and try it on your own if you like, or just keep listening and I'll explain my way through it here. So in the exploration, we're asked to identify on which intervals f of x is increasing. I think that's pretty self-explanatory there. You can just see there where is the function going up as you go from left to right, right? For b, same idea, except where is the function decreasing or going down as you go from left to right. Number 3, we're then asked to find what separates these intervals. Well, if you look, so for example, the first interval that the separation there is at negative 4. What is at negative 4? Well, you could call that a critical point, but it's also a relative extrema, right? It's a relative minimum. The next one at negative 3, also a critical point or relative extrema, relative max. At negative 1, the next separation point, relative minimum, right? And then at 3.5, roughly, that's again a relative extrema. Okay, and we'll see some more relationship with that in a little bit here. Step 4, we're asked to then say what is true about the slopes of the tangent lines at each value of x in the intervals in which the function is increasing. Or in other words, what kind of slopes do the tangent lines have where our function's increasing? Well, everywhere the function is increasing, these are all positive slopes. Everywhere the function is decreasing, we won't expect negative slopes, and that's true in general. And so, in fact, that little exploration there leads us to this theorem, which will hold true in all situations. If f prime of x is greater than 0 for all x in AB, then f is increasing on AB. If f prime of x is less than 0, that is negative for all x in AB, then f, the original function, is decreasing on AB. And if f prime of x is equal to 0 for all x in AB, then f is constant on AB. Okay? So we can now use the derivative and the sign, SIGN sign. If the derivative is positive on a certain interval, then the function is increasing on that interval. If the derivative is negative on a certain interval, then the function is decreasing on that interval. And finally, if the derivative again is 0, then that function we would expect to, the original function we would expect to be constant on that interval. Of course, we have some prerequisites here. The function needs to be continuous and differentiable to say these things. Okay, so then we go through some problems here after we discuss some guidelines. Okay, so some guidelines for finding intervals on which a function is increasing or decreasing. All right, we let f be continuous on the interval a to b, again to kind of match what we needed for the prerequisite there. To find the intervals on which f is increasing or decreasing. Okay, so the first thing we want to do to find the intervals on which f is decreasing or increasing, well, again, we just saw that here, right? What do we need to determine when f is increasing or decreasing? We need to know the sign of f prime. So given the function f, we should first go about finding f prime. Okay, once we've got f prime, then we're going to find those critical numbers. Okay, where do critical numbers occur? All right, so critical numbers occur when the derivative is 0 or undefined. Don't forget the undefined part, right? That's super important, super important. Both situations result in critical points, critical numbers. Number 3, create a line chart to determine the sign of f prime and the intervals between the critical numbers. So for example, what do I mean by the line chart? Well, we've seen line charts before. For example, when we solve these quadratic inequalities, right, we would factor so it's equal to 0, and then we'd find the zeros and plot those on a number line, and then we would pick numbers in each interval to test in the inequality to see if it made it work or not work, and those would be that's how we find our solution sets. In this case, we're going to look to see whether the points in between make the derivative positive or negative, and then again, that will be our increasing, decreasing behavior intervals. All right, and then finally, number 4, where you find the intervals where you find that f prime is greater than 0, you're going to say that f is increasing. Where you find the intervals when f prime is less than 0, you're going to say that f is decreasing. Okay, so again, positive derivative, your original function is increasing. Negative derivative, your original function is decreasing. Okay, positive first derivative, f is increasing. Negative first derivative, f is decreasing on those intervals. So let's actually do it, right? So here we find the intervals on which f of x is equal to x cubed minus 3 halves x squared. What's our first step to find the intervals of increasing or decreasing? Take the derivative. So the derivative of f of x is here, 3x squared minus 3x. Set it equal to 0 to get your critical points. How do we solve this? You need to factor. Do not add the 3x over and divide both sides by x. Factor. Set each factor equal to 0 using that zero product property to get 0 and 1 for your critical numbers. Okay, put them on a number line, and then you pick numbers in each interval here to test back into the derivative to see if you get a positive value or a negative value. You don't need to know the actual value, just whether it's positive or negative. So for example, I chose -1 here to test. 3 times -1, -3, -1 minus 1, -2. So -3 times -2, positive value. Negative times a negative is positive. Here I chose 1/2. 1/2 times 3 is positive 3. 1/2 minus 1 is negative, so positive times a negative is negative. And then same thing for 1, I chose like 2, I think. 2 times 3 is 6, so that's positive. 2 minus 1 is positive, so positive times positive is positive. Okay, positive. So we now have that the derivative, f prime, is positive for this entire interval from -infinity to 0. The derivative, or f prime, is also positive for this entire interval from 1 to infinity. So, since the derivative is positive there, f is increasing from -infinity to 0 and from 1 to infinity. What's the justification? I added the justify in there because we can also justify. Because f prime is greater than 0 on these intervals. You may not just say, refer to the chart, okay, for your justification. You need to write, because f prime is greater than 0, to justify that f is increasing here. Okay? F is decreasing on the interval from 0 to 1, because f prime is less than 0 on this interval. All right? All right, example 2, same situation here. Take the derivative, make sure you use a chain rule there, set it equal to 0, set each factor equal to 0, solve, and you get these values. Okay? The one little caveat here, or exception, is that we are on an interval from 0 to 2 pi, so I put 0 and 2 pi as the endpoints of my number line, and then put all the zeros or critical points in between there. Okay? Same thing, pick numbers between in your intervals there. Okay, these end up being all the quadrants, right? There's quadrant 1 from 0 to pi over 2, quadrant 2 from pi over 2 to pi, 3 and 4, so on and so forth. So pick a number, plug it back into the derivative to check. Okay, plug it back into the derivative here or here, it doesn't matter. So in this case, for first quadrant, it ends up being negative, positive, negative, positive. Okay, I chose like pi over 4 here, I think, for this one, and then some other ones there. Okay, with these results, then we can see that these two intervals, since f prime is negative, then f is decreasing on those two intervals, and then because these two intervals are positive, then f is increasing on those two intervals. I didn't put the justification there because, well, I think it's the same kind of justification as before. So, okay, example 3. The derivative of a function f is given by this. So this, we already have the derivative here. We don't actually have to take the derivative. It's given to us. On what intervals is f, the original function, decreasing? Okay. F is decreasing when what is true? F is decreasing when f prime is negative. How can we determine when f prime is negative? Well, we use our calculators. Okay, this is a calculator active question. So you're going to graph this in your graphing calculator. Let me grab mine here. All right, I already have it prepared, like a good chef on a cooking show. Pre-prepared example here. All right, typed in. We go to the graph. I already have it nice and graphed there for us. You'll notice that my window maybe looks a little bit different than yours. When I graph this, I changed my window to be 0 to 9. Why? Well, because it only asks us to identify the behavior of the function from 0 to 9. So I went ahead and blocked off all the other junk there. Okay. Now we got to be careful here. This is the graph of f prime, the derivative of f. We are trying to determine when f is decreasing. Okay? So f is decreasing when f prime is negative, right? So where is f prime negative here? Well, it's when it's below the x-axis, right? This is f prime, so where is it negative? F prime is negative when it's below the x-axis. So I'll do second trace. We'll do the 0 command. We can already see that f prime starts out negative. So we're going to start our first interval from 0, and we got to find what this 0 is right here. This x-intercept is. It's about 0.633. So our first interval of negativity is from 0 to 0.633. Well, there's only one answer that has 0 to 0.633. Everything else does not have that. So it's got to be A. Okay? If you check the other interval here, 4.115 to 6.916, that would be those two right there. Okay? So again, this is the graph of f prime. So we want to look when f prime is negative. That means when the graph of f prime is below the x-axis, to determine then when the original function is going to be decreasing. So that interval. Okay? Now, you'll notice here on my paper that I've drawn a line and put the word quiz above it. That means everything prior to this line is game for the quiz. Everything after this line is not going to be game for the quiz, or not, possible to be on the quiz. All right? So keep that in mind as we proceed on here. Okay. So our first bit of stuff that's going to follow the quiz here, follow the quiz topics, is the first derivative test. All right, we're now going to take that information we talked about, relative extrema, and we're going to relate that to the intervals of increasing and decreasing. If c is a critical number of a function f, then f of c can be classified as follows. If f prime of x changes, so if the derivative f prime changes from negative to positive at c, okay, so let's just pause right there. If f prime changes from negative to positive at c, that means f is changing from, well, if f prime is negative, decreasing to increasing. So f is changing from decreasing to increasing, which is something like this, right? Decreasing to increasing. Well, what does that locate? At c, that would be a relative minimum, right? Changing from decreasing to increasing is a relative minimum of f. If f prime changes from positive to negative, that means f is changing from increasing to decreasing, increasing to decreasing. That indicates a relative maximum there. Okay, that indicates a relative maximum. So, find the relative extrema of x times e to the 2x. When we go to take the derivative of this, be careful. This is a product rule. Product rule here. So second e to the 2x times the derivative of x, 1, plus the first x times the second, derivative of the second, e to the 2x times 2. Okay? Both of these terms have an e to the 2x. We can factor that e to the 2x out, leaving e to the 2x times 1 plus 2x, right? There's the 1 left over and the 2x left over there. Set each one equal to 0 to find those critical points. Okay? But e to the 2x never equals 0, right? E is like the number, it's like 2.6 something, okay? Raised to the 2x power Well, if you raise a positive number to a power, you can't get 0. It's just impossible. You can't multiply a number by itself a certain number of times to get 0. So the answer is never, never there. But 1 plus 2x can be 0, and so when x is negative 1/2. So you have one critical point when x is negative 1/2. Okay? We'll then check our intervals here. So I checked like negative 1 here. I think I checked 0 here. We'll plug those back into the derivative here. So plugging negative 1 in, e to the negative 2, it's going to be positive. Okay? It's okay. The power is negative, but that means the value still will be positive because it's e to a power, positive number to a power. It's going to be positive. And then 1 plus 2 times negative 1. Well, 2 times negative 1 is negative 2, plus 1 is negative 1. So it's negative times a positive, and it's going to be negative interval. Whereas if we check something like 0, e to the 0 is 1, not 0. E to the 0 is 1. 2 times 0 is 0, plus 1 is 1. So it's positive times positive. So the overall interval there is positive. Okay? Positive. All right. So that means since f prime is negative, f is decreasing on this interval. And since f prime is positive on this interval, f is increasing. So we change from decreasing to increasing. Decreasing to increasing. Relative minimum of f at x equals negative 1/2. And for the justification, because f prime changes from negative to positive at that point. That is a good justification and a sufficient justification for your answer. Okay, that's the only place where I justify there, but you get the idea of justifying for the other ones. It's a similar idea. Okay, number 5, also, okay, we also identify the intervals here. So you take the derivative, product rule, there it is, set it equal to 0. Okay, there's some GCF here we can factor out. So both of them have an x plus 3 in common. Both of them have an x minus 2 quantity squared in common. So we factor those out, and what's left behind is a 3x plus 3, and then plus 2x minus 2. Okay, we then combine like terms here in the square brackets to get 5x plus 5 and set each one of these factors equal to 0. So we get 2, negative 3, and negative 1. Create your number line. Okay, check numbers in your intervals back into the derivative. We get plus, minus, plus, plus. What? That's right. Your intervals don't always alternate. So please don't assume that they do. All right? They did back here, minus, plus, minus, plus. They did here, plus, minus, plus. But they don't always alternate. So do not assume that. You need to check every interval. You need to check every interval. All right? So with this behavior then, since f prime changes from positive to negative, f is changing from increasing to decreasing. So that is a relative maximum at negative 3. Here, since f prime is changing from negative to positive, that means f is changing from decreasing to increasing. So minimum at negative 1. And then at 2, since they're both positive, since f prime is positive on either side of 2, there's no change in behavior. It's just strictly increasing through there, so there's no relative extrema. So just relative extrema at negative 1, negative 3. Okay, again, showing that critical point doesn't necessarily have to be a relative extrema. Okay, but every relative extrema is a critical point. All right, number 6. Find the relative extrema of the function f given f prime of x is negative 4x over cube root of x squared minus 4. So we're finding the relative extrema of f, but we're given the derivative already. So we don't have to take the derivative. That's nice, because this would have been a yucky derivative to take. All right, with the quotient rule and all that stuff. So instead, we'll use the derivative here. Okay, we've already got it, so we're going to set the derivative equal to 0 to find our critical points. It's when negative 4x equals 0 or x is 0. But don't forget, critical points are also where the derivative is undefined. That's when the denominator would be equal to 0. So we cube both sides, add 4, and then square root, you get plus or minus 2. And so then there are our zeros on the interval. Okay? And so again, we check points in those intervals there. Okay? So we get plus, minus, indicating then that we have relative maximums at negative 2 and 2 because our derivative changes from positive to negative, and therefore the original function is changing from increasing to decreasing. And then we have a relative minimum of f at 0 because the derivative changes from negative, the f prime changes from negative to positive, or in other words, f is changing from decreasing to increasing. So a relative minimum there. Okay? And that's as far as we got. We did not get up to 7 or 8. I will finish 7 and 8 tomorrow in class, and then we'll be moving into concatenating the second derivative test as well tomorrow. Okay? And we should get through all of that by the end of the day, hopefully. Okay? Or get caught up at least. So, thanks for watching. Sorry that it had to be so abbreviated, and I probably talked even faster than I normally do, but I wanted to make sure I got that video done. All right.